let's assume that we have two vector spaces, this vector space V and this vector space W. A linear transformation from V to W is a function that takes vectors in V into vectors in W, and that it satisfies the following two operations. T of B1 plus B2 equal to T of B1 plus T of B2, and T of lambda times V is equal to lambda times T of B. Notice that this plus here is taking place in the vector space V, while this plus here is taking place in the vector space W. Same thing here. This lambda times V is taking place in the vector space V, is the multiplication by a scalar in V, while here we are multiplying a vector in W by a scalar. Then this is the definition of a linear transformation. Maybe the most basic example is when we have a matrix that is an n by m matrix. Then this function that we considered before, which we call T of A, that goes from Rm into Rn. We can also think of the function if the matrix has complex entries, or even if it has real entries, we can think more generally that it goes from Cm into Cn. Then this function is a linear transformation. Remember that the definition is we take a vector in Cm and we multiply it by A. Remember, this is an n by m matrix, and when you multiply it by a m by 1 matrix, which is this vector, we get a n by 1 vector, which is an element in Cn. We can show that in general almost every linear transformation is essentially given by a function like this, and that happens when these two vectors spaces, they have finite dimensions. Let's suppose that V has dimension of V, let's suppose that is m, and let's suppose that here we have a basis B1 Bm, and let's suppose that W it has dimension of W equal n, and let's suppose that here we have a basis W1 Wn. Then we can define the matrix representation of any linear transformation, and that is given in the following way. And let me just erase everything and explain what is the matrix representation of a linear transformation. Okay, this is the matrix representation of a linear transformation with respect to this basis. Let's suppose that this is the basis B, and let's suppose that this is the basis gamma. Then we're going to define a matrix, which is an n by m matrix. Then first of all, this is a matrix. This is an n by m matrix. And here m is the dimension of the domain and n is the dimension of the codomain. And the way to do it is we're going to describe the columns of this matrix. Then column number 1, let me just write, column number 1 is the coordinates of the vector T of B1 with respect to the base gamma. And then column number m same thing, is the coordinates, or maybe I should say the coordinate vector of T of B sub m with respect to gamma. That means that our matrix A is given by the first column are the representation of gamma of the vector T of B1. The second column is the representation with respect to the basis gamma of T of B2. And the last column is the representation of gamma of the vector T of Bm. Notice that T of B1 is a vector in W, then it makes sense to talk about the representation with respect to this basis. Let's do an example. Let's consider this transformation from matrices 2 by 2 into polynomials of order 2, and let's suppose that T of the matrix A, B, C, D is equal to A plus B plus C times X plus D times X squared. Then we can check that this is a linear transformation, it satisfies both properties. But then let's think about some bases for these spaces. We can pick any basis and do the representation, but let's pick the easiest basis. For M2, for matrices 2 by 2, I'm going to pick the bases 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And for polynomials of degree 2 or less, I'm going to pick the basis gamma equal to polynomial constant 1, polynomial x, and polynomial x squared. Notice that the dimension of P2 is 3, is the number of elements in a basis, and the dimension of matrices 2 by 2 is 4. Then we are going to get a matrix 3 by 4 matrix. Let's see what matrix is that. Actually here is, this is all that we need to know. Then how do I find the first column? Then what it says is compute the transformation at the first element. Let's compute T of, let's call this B1, B2, B3, B4, and this W1, W2, W3. Then I compute T of B1. To compute T of B1, I notice that A is 1, B is 0, C is 0, and D is 0. Then I get the polynomial 1, right? And what is the representation of this one? Representation with respect to the basis gamma of the polynomial 1. And then in order to find this representation, I have to write 1 as a linear combination of these three vectors, and I can accomplish that by saying 1 times 1 plus 0 times x plus 0 times x squared. These weights, 1, 0, and 1, 1, 0. These weights are the coordinates of this vector T of B1 with respect to the basis gamma. And then this is going to be my first column of my matrix. See, the first column of the matrix is the representation of T of B1 with respect to the basis gamma. To compute the second column, I have to compute T of B2. But this is T of this matrix 0, 1, 0, 0. And that means that A is 0, B is 1, C is 0, and D is 0. And then I get again 1. And then I have to write 1 as a linear combination of these three vectors, and then the weights are going to be the coordinates. I already did this. And then I will get again 1, 0, 0. What is T of B sub 3? T of B sub 3 is T of the matrix 0, 0, 1, 0. And in this case, everything is 0 but C, and then I get the polynomial x. And when you think about this, this is just 0 times 1 plus 1 times x plus 0 times x squared. That means that the representation of, with respect to the basis gamma, of the vector x is 0, 1, 0. And then this is the column, this is my third column of the matrix. And finally, if I do, let me erase this one. If I do T of B4, T of B4 is T of 0, 0, 0, 1. And then this is what I get when A is 0, B is 0, C is 0, and D is 1. And then I get 1 times x squared. And clearly, the representation of this vector with respect to this basis is just the vector 0, 0, 1. That means that this matrix is the representation of this transformation with respect to this basis and this basis. Something that is going to be important is that most of the information about the transformation T is in this matrix. Maybe the most important property for the matrix that represents a transformation is the following property. If B is in B and the representation with respect to the basis B of little b is the vector alpha 1, alpha m, then when I do A times this representation, I get a vector in Cn. Then I get n complex numbers. And the theorem says that this vector is just the representation with respect to gamma of the vector T of P. Then this is the important theorem about the matrix representation. Maybe we can do an example to illustrate this property. Let me erase this. And let's take a matrix. Let's suppose that my vector V in this vector space is the matrix 3, 2, negative 1, 4. Right? Then when I write the representation of this vector with respect to my basis B, I notice that this matrix can be written as 3 times B1 plus 2 times B2 minus B3 plus 4 times B4. And therefore, these weights are going to be the representation of V with respect to the basis B. Then this representation is 3, 2, negative 1, 4. This is the alpha 1 up to alpha 4. Then, if I multiply this matrix by this vector, what do I get? If I multiply 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1 times 3, 2, negative 1, 4. What vector do I get? I get 5, and then negative 1, and then 4. And what the theorem says is that these three numbers give us the representation of T of B. Let's see that. These three numbers are the representation of phi times, if I use the base gamma, it will be phi times 1 plus negative 1 times x plus 4 times x squared. These three numbers are the representation of this vector. But on the other hand, this is supposed to be equal to what I get when I do T of B. What do I get when I do T of B? If I do T of B, A is 3, B is 2, C is negative 1, and D is 4. Then I get A plus B, which is 5, and then C, which is negative 1, plus D, plus 4x squared. Then this is the important part of the representation of a linear transformation with respect to some bases. Then, this is the theorem. Let me just rewrite it. It says that the coordinates with respect to the bases in the codomain of T of a vector is just the matrix times the representation with respect to the bases in the domain of that vector. This is the important part.